Welcome back. I hope you tried the exercise yourself. Let's start with the third question. So this is the Earth, and this is object A, and the question was, does the Earth exert a stronger gravity force on object A or vice versa? Does object A exert a stronger gravity force on the Earth? That was the third question. Well, remember the Newton's third law. According to this law, if the Earth applies force on object A, then object A applies force on the Earth, and they have the same magnitude, the same strength, but they are opposite in direction. And so let's imagine that our inertia frame is right here, and so the Earth and then object A, they move with respect to this inertia frame. And so in this inertia frame, we can write that the force of gravity that Earth applies to object A, its magnitude is equal to the magnitude of force of gravity that object A applies to the Earth. Or we can simply write that you have the absolute values of F, and all that equals G times the mass of the Earth times the mass of object A divided by r squared, and this r, it's the distance between the centers of the Earth and object A, assuming that our mass distribution is equal here. Our densities are constant. Now, as a side knowledge, I want you to know that when people write something like this, F and then the arrow, then it's a three-dimensional vector. But when they write the absolute value of F vector, then it's the magnitude of this vector, and you can calculate this magnitude like this: fx squared plus fy squared plus fz squared, and then you take the square root of everything. And so in this inertia frame here, the acceleration of object A towards the Earth is the following. If this is our force formula here, then I can also rewrite it like this: the absolute value of F and then mass of object A times and then everything else. And so you know that when mass is constant, then F equals m times acceleration. So in this case it would be the mass of object A times the acceleration of this object A. And so that means that this part here, that's the acceleration of object A. And this acceleration here, it's with respect to this inertia frame, which itself doesn't accelerate. It's fixed here. So that's question 1. Question 3, it was this one here. You saw that the forces that both objects exerted on each other, they had the same magnitude, and then they were opposite in direction, according to the Newton's third law. And then the first question, it was this one here. That's the acceleration of object A with respect to this inertia frame. In other words, object A accelerates towards the Earth, but it's important to understand that this acceleration is measured with respect to this fixed inertia frame, not with respect to the Earth. And that's because the Earth also moves a little bit with respect to this inertia frame. And then question number 2 was, what's the acceleration of the Earth towards object A? Well, again, this is our force formula, but now I'm going to write here the mass of the Earth times G times the mass of object A divided by r squared. So now in this case, assuming that the Earth's mass is constant, the force formula would be the mass of the Earth times the acceleration of the Earth. And so this one here, that's the acceleration of the Earth towards object A, and again, this acceleration is with respect to this fixed inertia frame. So both objects, the Earth and object A, they move with respect to this inertia frame. And so that's the answer for question 2. As you can see that in both cases, the accelerations depend on g, then the mass of the other object, so the acceleration of object A depends on the mass of the Earth, and the acceleration of the Earth depends on the mass of object A. And then both of them depend on the distance between them, between their center of gravities, that in our assumption are located in the centers of those both objects. Now, I have been reiterating a lot that these accelerations here, that they are measured with respect to this inertia frame. However, for the purposes of statics and dynamics, we should know the acceleration of object A with respect to the Earth, not with respect to this inertia frame, but with respect to the Earth. And you can calculate that like this. The acceleration of object A with respect to the Earth, it equals the acceleration of object A with respect to the inertia frame minus the acceleration of the Earth with respect to the inertia frame. So again, this one here, that's the acceleration of object A relative to the Earth, not relative to this fixed inertia frame. Imagine that you have two cars. This is car A and this is car B. And so here I have my inertia reference frame, which is fixed. Let's imagine that car A drives in this direction at 30 meters per second. And then car B, it drives in this direction at 40 meters per second. These velocities, they are with respect to this fixed inertia frame. Car A drives in the positive x direction and car B drives in the negative x direction. And now, how fast does car B travel relative to car A? Pause the video for 20 seconds and calculate what's the velocity of car B with respect to car A. What would it be? Well, the velocity of car B with respect to car A, that would be the velocity of car B relative to the inertia frame minus the velocity of car A relative to the inertia frame. The velocity of car B relative to the inertia frame, it's minus 40 meters per second because it goes in the negative x direction, and then minus, and then you have plus here, and then 30 meters per second. That's because car A travels in the positive x direction. And you will get minus 70 meters per second. So relative to car A, car B travels 70 meters per second in the negative x direction. You can think of it like this. You can imagine that car A now is at rest. So this is your car A. Now you imagine that your car A is at rest. So I can put an inertia frame here. And then car B travels at minus 70 meters per second or 70 meters per second towards car A. Now it travels 70 meters per second in the negative x direction, but this x is now attached to car A. And so it's just another way to think about it. When cars crash, then this velocity here is more important than these velocities here. And the same thing here with these planets. It's exactly the same logic. The acceleration of object relative to the Earth, it's calculated like this, with this formula here. And now, since you know this one, which is this one here, and you know this one, which is this one here, you can say that v dot and then a relative to e, it equals minus g times the Earth's mass divided by r squared, which is this one here, and the reason why you have this minus sign here is because the acceleration of object A with respect to the inertia frame is in the negative x direction, and then you have minus, and then you have plus, and then g times mass A over r squared. So that's the acceleration of the Earth with respect to the inertia frame. And it's positive because it accelerates in the positive inertial x direction. And then of course we can simply rewrite it like this, minus g, and then you can put r squared here, and here you will have mass E plus mass A. So just like we did it with the car, we can imagine that this is our Earth, and we're going to put a fixed inertia frame right here. We're going to attach it to the center of the Earth. I'm going to call it x sub e, and y sub e. It's fixed to the Earth, and now this is object A, and now here you consider that the Earth is fixed, and the acceleration of object A relative to the Earth, it's this one here. That's what you had calculated here. Now the thing is that if m sub e, that's the mass of the Earth, and m sub a, that's the mass of, let's say, the Moon, then even though the mass of the Moon is smaller than the mass of the Earth, it's not negligible. The Moon still has considerable amount of mass compared to the Earth. Then this formula here makes sense. However, if this mass sub a, if it's the mass of a satellite or an airplane or a structural beam, well then the mass of object A is so small compared to the mass of the Earth that it's almost nothing, it's negligible. In that case, we can simplify this equation. We can just say that this m sub a, that it's 0 kilograms, and that means that the acceleration of A relative to E, it's approximately minus g times the mass of the Earth divided by r squared. And so now, when we consider this x sub e and y sub e as our reference frame, which is the inertia frame, then in that reference frame, the Earth is fixed in place, and the force of gravity that is applied to this object in that reference frame, which is attached to the Earth, this force of gravity, it can be written like this: the mass of object A times the acceleration of object A relative to the Earth. In other words, you have m sub a times, and then all this, which is your acceleration. Or, if we simplify it, because mass sub a is simply so much smaller than mass sub e, then we can say that this force of gravity, it's approximately mass sub a times, and then g times mass sub e over r squared. And I've simply taken this minus sign and I've put it here. Or, if you're interested in its magnitude, then you can put it all inside these absolute value signs, and you can write all that like this. Now, of course, in reality you have 3 dimensions. You have x sub e, y sub e, and then you have z sub e. But here we are assuming that this z sub e, it comes out of the screen towards you. And now, if you're at the latitude of 45 degrees and you're at sea level on planet Earth, then this v dot a relative to e, the acceleration of object A with respect to the Earth, which is approximately this one, then it has been measured to be approximately 9.81 meters per second squared. And that's the famous g, or the gravitational acceleration on the surface of the Earth. And that's what we will use in our statics and dynamics problems. It's measured at 45-degree latitude because the Earth is not a perfect sphere in reality. It's wider on the equator and narrower on the poles. And so that means that your r here, it will be a little bit bigger when you're on the equator and a little bit smaller if you're on the poles. And obviously your r is also different when your altitude is different. When you are on top of some kind of mountain, then that will increase this r variable. And all these things make your g different, even though the differences are negligible. But in order to have one standard universal number for your g, it was agreed that it would be measured at sea level and at 45-degree latitude, which is this angle here.